Hello, and welcome to SUSECON Digital's presentation of Ceph in a Windows World. I'm Mike Latimer. I'm an engineering manager here at SUSE, and joining with me is Alessandro Pelotti, who's the CEO and CTO of Cloud-Based Solutions, who's an important partner in this project that we've got going on. We're both very excited to be able to speak on this topic. We would have really preferred to do it in person to get real-time feedback and comments and questions regarding our efforts here. But as that's not possible, feel free to use our contact information here to reach out with more questions or comments that you might have. I'll start by quickly covering the agenda. Since I can't reach out to you and talk to you directly, we're going to go ahead and do a quick overview of Ceph to make sure we have a fundamental understanding of Ceph terminology that we'll be using later in the presentation. And then we'll talk about challenges in the Ceph and Windows integration environments, and also SUSE and Cloud-Based Solution, how we've partnered together to address some of these issues. We'll finally talk about sample use cases and some of the demos. Alessandro's prepared some demos to actually showcase the product, so we're looking forward to being able to share that. So first of all, Ceph is known for being a highly scalable and resilient distributed storage system that can be built on commodity hardware. And I say commodity hardware in quotes because in reality, if you use 10-year-old hardware to create a storage solution, it's going to reflect the behavior of hardware from 10 years ago and the performance characteristics of that. So in reality, you want to use performant, good quality hardware to build your Ceph cluster, but that should be fairly obvious. Anytime you cluster machines, you end up with a distributed system, but it's the way Ceph achieves their highly scalable and resilient aspects that are kind of more interesting here. It's Ceph's underlying design that gives us the scalability aspects through something called RAIDOS, which is Reliable Autonomic Distributed Object Store. Obviously, that's a bit of a handful or mouthful, and so I'm going to just stick to calling it RAIDOS. Central to the RAIDOS architecture is an algorithmic method for reliably predicting where data is distributed across the cluster. This is known as the crush algorithm, and it creates what is known as the crush map for determining where data is actually located. But it's the fact that it's predictable that is interesting and key to its success. Ceph clients use this algorithm and the crush map to determine for themselves where the data can actually be found within the cluster. And then they access that data directly from that storage location. This allows Ceph to scale very well to hundreds or thousands of nodes and devices. Resiliency is provided through the ability to create replicated or erasure-coded storage pools, and a crush map that is created with resiliency in mind also takes into account the concept of failure domains to ensure that multiple copies of data are written across multiple points of failure. For example, you can define a server rack or a room as a failure domain, and then ensure your data is secured across the failure of that particular area. Data within the Ceph cluster itself is accessed through object, block, or file storage method interfaces. Object storage is typically through an S3 or Swift compatible gateway, which provides an HTTP API interface on the front end and uses librbd to connect to Ceph itself on the back end. Block storage is through a Linux kernel module or librbd. And that is effectively similar to what ISCSI does, where it presents an RBD image to a client, which can then consume and access as a local block device. File storage is available through CephFS, which can be either a kernel module or a Fuse client through a couple of libraries, a combination of libceffs and librados. And that basically appears, that presents a POSIX compatible file system similar to the way that you're used to with NFS. If you were to look at the very simplified architecture of Ceph, which is described here in this image, you can see across the bottom we've got object storage devices, 6 object storage devices or OSDs. These are individual disks, which are then grouped together to the RAIDOS layer above it. And then that's effectively the Ceph cluster itself. Interfaces into the cluster can be really divided into these three examples of how applications can interface into the cluster itself. The first is direct access through librados. This library, the librados library, understands CrushMap and provides direct access to data residing within the cluster. Some examples of this would be the gateways, so the S3 or the Samba gateways, which use librados very effectively to directly contact those members of the cluster. The next method is block storage through librbd. This method connects a local block device to a Rados block image. Again, this is similar to the ISCSI sort of model. And it's very commonly used for virtualized environments where you're serving up a disk image to a virtual machine as local storage to that virtual machine. The last method in this architecture overview here is just file system level access through Cephfs, and clients effectively consume that, as I mentioned before, just through a local mount that gives them a directory listing of the contents of the cluster itself. It's possible to take these interfaces and divide them into two broad categories, gateway versus native. In the gateway category, we have the gateways that I mentioned before, the ISCSI, the Samba, and the S3 gateways. In this model, a gateway is effectively serving as a proxy to the cluster for clients that don't understand how to speak natively to the Ceph cluster itself. The gateway itself, the ISCSI device in this case, or Samba or S3, they understand Rados environments, they understand how to use the CrushMap, and they themselves have direct access to the cluster resources, but the clients are using industry standard protocols just to connect to ISCSI. So there's some loss there. All traffic has to flow through that gateway to gain that knowledge of how the cluster actually works. Native access is the preferred way of connecting to a Ceph cluster. This ensures that full knowledge of the CrushMap and correspondingly where data is located is available on the client itself. And this results in better I/O throughput, as clients can connect to multiple OSDs as necessary, and eliminates that single point of failure. I wanted to help understand this better just through a couple of simple diagrams. This is the first one that shows the basic I/O path from clients on the left to an RBD image on the right, which is spread across multiple OSD devices. In the middle, we have the ISCSI gateway itself. And you can see that the clients connect to the gateway. In this case, in the ISCSI case, we've got initiators on the client connecting to the target that the ISCSI gateway serves up. And the gateway speaks librbd directly to the individual OSDs involved with serving up that RBD image to those clients. If you were to take this and switch to a native I/O model, it looks more like this, where librbd is actually an integral part of the client itself, and that eliminates the gateways being the central point that provides access to the RBD, and the individual clients can directly contact the OSD devices which are holding parts of that RBD image itself. So this model completely removes the potential CPU and I/O bottlenecks that you get in the gateway model. As we know, there are many statistics that show the overall penetration of various operating systems in enterprise environments. This quote from Gartner shows that Microsoft Server is obviously still a very relevant part of the market, and many of our customers do use Microsoft environments. And therefore, this is kind of one of the driving reasons behind this project. We wanted to take the great experience that Linux users are used to encountering in Ceph environments and make sure Windows users were able to have that same great experience. So when you do go to a Windows environment, there are two basic ways that we see people use Ceph resources. And in both cases, they're through gateways. One is through the ISCSI gateway, and another is through the Samba gateway. And they both have various use cases where they're a little more interesting in one scenario versus another. But ISCSI provides that block device to support that people use in Hyper-V environments, or simply a scenario where we're taking a block device and serving it up to the Windows server itself. Windows Server, they consume that. And you can actually use your typical Windows Server management tools to treat it as any other disk and partition it and put the file system that you want on it. An important thing to point out here is there is no direct client to OSD connections because they all have to go through that ISCSI gateway. From a Samba perspective, this provides file access similar to Ceph FS, well, similar to NFS or Ceph FS from a Linux perspective. It requires a Samba Gateway. It provides some advanced features, the multi-protocol support, and it maps Windows SIDs to Linux UIDs. So there's a use model different. If you want a block device on Linux, a block device served up from Ceph to your Windows machine, you would use the ISCSI gateway, and if you need the file system access itself for home directories or whatever, the Samba gateway provides access to this. But once again, we have the same limitation where no direct client to OSD connections are allowed or provided. So as we looked at this environment and helped our customers work through some of the challenges in those environments, we kind of realized that the best way to address these limitations is to simply port Ceph to Windows environments and gain that native support that Linux benefits from. Cloud-Based Solutions is a company with a long track record doing just that, porting cloud-related open source projects to Windows. They've done this with OpenStack, Open vSwitch, Crowbar, Kubernetes, and now Ceph. SUSE and Cloud-Based have collaborated together for many years, so it's really just a matter of time until our partnership started on this highly demanded porting project. Let's now hear directly from Alessandro on their efforts so far.
Okay, thanks, Mike. So, as Mike said, this is definitely something that the industry was requiring since a long time and something we want really to do since a long time. And we are really happy about this partnership with SUSE to being able to bring it to market. The main problem, of course, as Mike mentioned, is the fact that you will never get proper performance on Windows if you just go to the ISCSI gateway part. So the right way to do it was to just port seamlessly RBD to Windows, which is exactly what we did. That means that we developed a set of fully open source projects, including, of course, a kernel driver, which will handle, of course, all the I/O. We have, of course, reported all the user space, command line interface surface that we need. And from a usage perspective, the Ceph operators, so people which have already Ceph experience, will find themselves completely at home, even if it's a completely different operating system. On the other side, people which come from a Windows experience, of Windows system administrators and so on, which are not necessarily particularly familiar with Ceph, will still find it perfectly integrated into the Windows world. And so it doesn't look like a piece of Linux, let's say, with sticks inside of a Windows operating system. It's everything seamlessly integrated. Actually, I'm really excited to share the few demos that we recorded for this particular session in a few minutes. So we ported librbd, we ported libRados. We have the block driver, as mentioned before, and everything is open source. So you will find it upstream in Ceph, and you will find us also working as part of the community. What else? Well, in terms of benefits, the performance is the primary one, as I mentioned already before. So you will find that, let's say that our goal is to reach pretty much the same performance that you have on Linux. So it should be completely seamless from a integration standpoint. Ease of deployment, no need for an ISCSI setup. It will be completely easy to deploy all the bits and pieces which are needed. So nothing different than deploying any other standard, let's say, storage technology on top of Microsoft Windows. And it will integrate with the Ceph cluster exactly like a standard Linux node will do. So you will just need your Ceph configuration file. You feed it to the service and the binaries that we have here, and it will just work independently. The compatibility will be absolute, meaning that at that point you will be able to use the block devices in the same identical way, and you will also be able to use FFS, as we will see during the demos.
Thanks, Alessandro. Before we get to the demo, I wanted to talk about just some of the targeted use cases that were the intent behind this effort. And they should be fairly apparent, There are a couple that are worth pointing out, though. First of all, from a Windows-based backup solutions, we know that Ceph is a very effective target for backup solutions, and many of these are running in Windows environments. Veeam is a great example of this that many of our customers use, and in order to use that, they generally use ISCSI block devices that are served up to Windows, and then Windows consumes those, and that's where Veeam stores the data. This can be a little complicated, and obviously, given the limitations of going having the I/O path route through the gateway, that's kind of a there's room for improvement there. This is also true for Microsoft Hyper-V and cluster server environments. Obviously, these are very large markets where lots of people are building solutions in these environments, and Ceph block devices. Really, if we're using the native tools, they're going to be a lot easier to create and manage, and performance should be significantly improved. So let's look a little bit further into the sample Veeam configuration that I kind of mentioned. This shows a configuration that we've seen many times, and we've helped customers with these configurations. And again, it's important to note that customers are having success with this today, and it's working very well for them. However, we simply believe there's ways that it can be improved. So in this example, we see on the left, we have several OSD devices that form the foundation of an RBD image. That RBD image is served up via librbd to multiple ISCSI gateways in the middle. On the right, we have a virtualization host that is hosting some kind of a Windows VM, and inside that VM, we have ISCSI initiators that are connecting to the targets that the ISCSI gateways serve up. Multipath is used to combine those into one logical path. In this case, it's an E drive, and Veeam writes that backup data to that E drive. So this all works today, but is somewhat complex. If we take a look at this same environment with librbd, you can see a significant reduction in complexity. On the right, we still see that Veeam still sees an E drive. It is still writing data down to a local disk that it sees. But instead of that being backed by multipath and ISCSI and through a gateway, we have librbd directly connecting to those native to those Ceph resources through native I/O paths. Obviously, this reduces a significant amount of bottlenecks and complexities, and should allow Veeam to be as performant as possible, and certainly improve the administrative experience of setting up such an environment. It is important to note that network speeds still matter. As I've been playing with the code and doing some benchmarking, in some of my tests, I've been actually doing just Windows machines that were several hops away from the actual cluster, which was running at 100 gigabit speeds. And obviously, you're never going to fully utilize or reach the capabilities of your cluster if you've got a gigabit switch in between the two. So it's just important to point out that the fact that we're moving to a different model, it's not going to negate the fact that the infrastructure itself still matters. And therefore, it's important to design the infrastructure to take that into consideration. So it's time for the demo, which I'm very excited to share with you. Alessandro's done a great job of putting some of these demos together. So this is what we'll be looking at next. And let's go ahead and just jump to it.
Hello, everyone. I'm going to show you a few demos about the porting of Ceph on Windows. I will start by creating an image. I will do it directly on Windows. So let's create our first image. So if I do an rbd ls, I will see that the image is there. So the next thing we need to do is to map it. So this one is called the Win1. And as you can see here on the left in the disk management, you can see that a new disk popped up. So all we have to do is to bring it online and initialize it. So initialize disk. And we create a volume. The next thing, you can see that we can see already the volume in our Windows Explorer. You can create a file, for example. Next, if you want to unmap it, if I map it again, you can see that it shows up again. It retains the same volume letter. So if I open Explorer, I find all my files again in the same place. And just to show you, here is, for example, an SSH client connected directly to one of the nodes in the cluster. And if I run the same commands here, I'm able to see the same data. Okay, so this is already the first start. So you can see we can create images and map them as block devices on Windows, which is fantastic, because we don't need to use any more an ISCSI gateway or any other solution to access the Ceph storage data. Next, I'm going to show you how CephFS works. So first we need to create a volume, an FS volume. Going to do that directly on Linux. Next, we can just use ceph-docken on Windows to mount it locally. X is going to be the name of our volume. So again, if I open Windows Explorer, I can see that it's there. So let's create a file. Hello, CephFS. Nice. Okay. Now let's move on the Linux side. And we can do the same. So in this case, we mount it on a local directory. And we can see that the file is there. There it is. Next, let's create also a file here. So hello from Linux. And here is the file. So you can see we have both files there. So if I refresh here, I can see the second file, and if I open it, I see all the content. So this is shared perfectly transparently across Linux and Windows. Okay, I have one other demo, one last one, in which I'm going to show you how we can use RBD image to boot a Hyper-V VM. So the first thing we need is QEMU. So we use just QEMU MG convert. So we're not using QEMU just to make sure here for running the virtual machine itself. We just use it to actually take the content of a QCOW2 disk and create an actual RBD image out of it. Okay, here it is. Next, we're going to look at the images that we have. So as you can see, I have a new one called Hyper-V. What we have to do is to map it on this side. So here it is. As you can see, we have a new disk which shows up here. It's already online. In this case, it already contains data because those are the partitions from the actual disk that we copied over from the QCOW2, the original QCOW2. So we have to put it offline. And this is just an OpenSUSE operating system with just an FOS. So here it's already mapped, as I mentioned before. We need to create a VM. We're going to call it SUSE1. And we're going to add hard disk drive in pass-through, meaning that the actual block device is going to be passed directly to the VM. This number is 2. As you can see, we're matching the disk that we have here. And then we can just start the VM. Voila. Let's connect to it. And as you can see, it's booting directly out of that image. There we go. We're going to just accept all the default here. Put the password. And here we go. Our VM is running directly out of the RBD block device. So thanks a lot for watching these demos, and I hope you like them.
Okay, so the demo showed you pretty much everything that we did until now. We're still work in progress, so there is a lot of work going on. Functionality and performance-wise, we're still working on file locking and ACLs. That's especially at the Ceph FS level, code level tuning and optimizations. You will see also that all the PRs are currently being merged upstream. So feel free, of course, to reach out, and we will be able to share with you all the bits and pieces so you can also try it out on your environments. Driver delivery installation mechanism is something which is we are working on. So whether it's going to be graphical installation tool, full automation, let's say integration with Ansible and other automation tools for the distribution and so on. This is something that, of course, we are still working on. And Mike?
Yeah, so I wanted to mention briefly pricing and availability. This is very much a work in progress. Our product managers are working diligently to interact with the customers and get feedback on this topic in order to make sure that that we're providing a solution that is great for you and your business, and obviously is a good value. We do expect this to be significantly less than the traditional storage model, which is true to our current SUSE enterprise storage offering in general. From an availability perspective, as Alessandro mentioned, we're working directly with upstream on getting those pull requests merged and working with them to make sure the code is acceptable. This is a fairly lengthy process, but we do expect to make good headway. The code has been partially merged and will continue to do so and continue to push to get that merged. And hopefully be able to announce a shipping date in the relatively near future. So keep your eyes on SUSE.com because I'm sure as soon as we do have those dates, we'll make sure it's very widely known. As we mentioned, we're very excited about this project. We're anxious to get this into people's hands. Thank you for paying attention and listening to this. If you do have any questions, feel free to reach out to Alessandro or myself or your local sales rep and put some pressure on them to make sure we deliver this as quickly as possible because we know that it is going to be a big benefit to you and your business. Thank you for listening.
Thank you very much.